So if you recall, yesterday we started with sigmoid neuron. We saw what is the function we use in sigmoid neuron and how exactly it is different than MP neuron and perceptron, right? Today we'll continue on that. And just to move ahead, let me give some of the more advantage that we have on sigmoid neuron compared to MP neuron. Okay. So, yeah. So if you recall, in case of perceptron, right, we had our point, right, distributed in x and y axis, and the points were like, right? So these are the one set of point, these are the other set of point, and our intention was to come up with a line that can segregate these 2 points, right? So MP neuron, what MP neuron was doing, it was giving us a linear line that can segregate these 2 points together, right? Now see, if we look this distribution carefully, what we were seeing that the point which is very closer to decision boundary, that is also equally important, whereas the point which is very far away from decision boundary, for example, if you look this particular point and this particular point, right? So what we were saying that both of these points will belong to category 1, whereas all these points will belong to category 0. Okay. Which is,
starting the class Brishit.
But do you think that this interpretation is 100% correct? Yeah, we can say that all the points which are in the one side of the decision boundary should belong to one class, the other set of points should belong to other class. But the points which are more closer to decision boundary, which are very closer to decision boundary, they are the points where we need to give a little bit think, right? Because by just some manipulation, this point could have gone to this side, right? So there we should have certain way of mechanism by which we can say that we are this much percentage of we are having this much percentage of confidence that this particular point will belong to category 1, and we have this much percentage of confidence that this particular point will belong to category 0. Unfortunately, in case of MP neuron or perceptron, we do not have this kind of mechanism. Anything which is above threshold straight away go to one set of category. Anything which is below threshold, it goes to the set of category, right? But in case of sigmoid neuron, we have this mechanism. Since we are able to calculate the probability value, right? We are able to get the probability value. We can say that all the points which are closer to decision boundary, they have lesser probability of getting into that particular category. For example, here let me draw this for sigmoid neuron. Right, I have, let's say, point here. Here this is x, and this is the probability score, and this is the category. Right. So if suppose the model of MP neuron is giving me a probability value, let's say it is giving probability value 0.4, will it be classified as 0 or 1? If my decision boundary is at probability score of 0.5?
It will be 0, right? If it's 0.5?
Correct. If, let's say I'm having x2, which is 0.9, where would it fall? Will it go to category 1 or 0?
1.
Yeah. Similarly, let's say I'm having 0.45, it will 0, x4, 0.5, 0.55, it will be 1, right? So if we'll plot this data into coordinate axis, right, you'll see that the point which we have the point for which we have very high probability score. So for example, we are saying that we are 90% confident that this particular point x2, it will go to category 1. So this point will be very far away from your decision boundary. Whereas in this case, we are just marginally classifying that this particular point will go to category 1. We are just 55% sure that this point will be going to category 1. So this point will be very close to decision boundary, right? The same goes on for negative point also. Since this point is very close to decision boundary, that means though we are saying that this will belong to category 0, but we're not really confident, right? So that is an advantage we are getting with sigmoid neuron. We're not only classifying the point as positive and negative, but also we are able to relate it with a sense of confidence. Just think of an example, a real life example. Let's say that you are working in some banking domain, right? Whereas a customer comes to you and he applies for loan. Your responsibility is to either grant him a loan or deny his application, right? Now let's say that for making these decisions, you are making the use of your sigmoid neuron, right? You have taken the details of your customer, you have fed into your system, and your system says that you should give him loan with the confidence or probability score of 0.55, right? Now here comes a twist. Now will you give him a loan or not, right? Or though your model is saying that you should give him loan because anything which is more than 0.5, it will be classified as 1, but here the probability score is just 0.55, right? So in that case, you will rethink some other parameters. For example, what is the loan amount? What loss I'll be having if the person default the loan? In that case, you need to do some more analysis to take this risk, because giving a loan to a person with 55% of confidence is not a good decision. But on the same time, if you deny his application, your bank might lose some business, right? So this is the place where this probability score plays a good role. It helps you to make an informed decision as a manager. You're getting this concept?
Yeah. So I have a question, Ashutosh.
Mm-hmm.
Yeah.
So as you're saying, as you're saying that the 55% is the probability, right? The result shows. So since it is still above the,
Hmm.
it's on the other side of the decision boundary, like
Hmm.
or towards the +1.
Mm-hmm.
That means we will still, we can take the decision of doing giving the loan, right?
Yes, you can take the decision of giving him a loan, but the point is you're just 55% confident. Your decision would have been more strong, more better if that probability score would have been something like 0.9 or 0.95, right?
So you're saying that the ability to classify these confidence is what this sigmoid neuron is giving us. Like
Correct.
a candidate can have 90%, can give us 90% confidence, whereas someone can give us 56% confidence.
Yes.
So that's the advantage you're saying that we are getting
Yes.
using. Okay.
Yep.
Okay, it's
Yep.
clear.
Right. Because see, ultimately, you can tie this probability score with a lot of things. You can tie this probability score with risk also, right? Giving somebody loan with 90% of confidence involves lesser risk compared to giving somebody with 55% of confidence, right? So this benefit you are getting it with sigmoid neuron. Now, if you look carefully in this particular figure, whatever I just explained you, it is summarized. It has been summarized here. So here I'm having two category of point. One is represented by red, other is represented by green. Are sigmoid neuron able to find a decision boundary which is somewhat here, right? So all the points which is lying on the left hand side of this line, it will belong to one category, that is green. All the point which lie on the left hand side, it belongs to one category, red, right? Now whatever point which are very close to decision boundary, right, for those point it is bit difficult to make decision, although we able to classify this point as green, but it could have gone to this side also with just a marginal change, right? That is why you see a color coding. More this point farther from this decision boundary, the better it would be, right? For example, this particular point is very far away from decision boundary. That means we are very much confident that this should go to this particular category, right? Ideally you should come up with that function which creates a decision boundary, and that decision boundary should be very far from your points, right? So that should be our goal.
So the goal is that all our points should be away from the decision boundary.
Yes, the goal should be we should come up with that decision boundary from where my point should be as distant as possible. Here if you'll see that although I have able to come up with one decision boundary, but the points are very close to decision boundary. That means that for those points we're not 100, we're not really sure to which side this point should go. Okay.
But why are you saying we are not sure? I mean, the algorithm is classifying them, right? That they
Yes,
belong or there.
Okay, so
but this is not a robust classification,
if we
right?
see there are
Just a slight change in your data, it can make this point move to that other side,
Yeah.
right? This is not a robust classification. This is not a feature of robust classifier. Yeah, so maybe you were saying something. Hello. Oh, okay, I think it was just a random noise. Okay. Now can you quickly answer this question? The decision boundary of sigmoid neuron is non-linear only when the weight of the neuron are tuned in such a way that we get an optimal decision surface that cover most of the data correctly.
True.
Yes, it's true. Okay. Now coming to the important point. So similar to perceptron, again the important parameter that we have to learn is W and B, right? So how the change in W and B is changing my function, that is something that we will be seeing in this slide. By the way, you all agree that here also the learning parameter is W and B?
Yeah.
yes.
Okay. So this is the sigmoid function I have plotted when my W was 3.5 and my B was 0. Okay. So here I am having only one input feature and I'll have one target. Okay. So with respect to one input feature, I'm having one value of W. So when my B is 0, you'll see that it will pass through origin. It will pass through x equal to 0. Okay. And you'll see that my y will be intersecting at somewhat around 0.5. Okay. So W is what? But before that, let us see the another plot. When my W is increased, when my weight is increased, you'll see that the shape of my curve has changed. Initially, the slope was, my slope was, if I have to plot a slope around this, my slope would be somewhat around vertical, right? But now when I have changed my value of W, keeping the value of B constant. Rather, I should say when my W is increased, right? So positive W, positive slope. Whenever my W is positive, first of all, my slope will be positive. That is one thing to note here, right?
And so you're changing W from 3.5 to 0.4.
Yes.
Okay. And like these are like just randomly you have picked these
Yes.
values?
Yeah, these are random picks.
Okay.
Right. Now see, as I will increase my value of W, this S shape will become flatten. It will flatten as the value of W will increase. Right? If you'll see in this figure, the shape of my curve has flattened compared to this one, as I have increased the value of W. Now, as
One second, Ashutosh, so you're saying when you're increasing, but isn't the value of W decreasing? I mean, 3.5 is greater than 0.4, right?
yeah, sorry. Yeah, I
It is
made an
decreasing.
yeah, I made an error here. Yeah. So when my W is decreasing, my this descent boundary is getting flat, right? Yeah, I was thinking maybe at 3.4 I'm having, but yeah, as my W is decreasing, my shape of function is getting flat.
Yeah.
Right. Now, what this B is controlling, when I am changing the value of B, which will come to the other slide. Yeah. When I'm changing the value of B, you will be able to shift your function, right? So what is happening? Increasing the value of B, shift the function to the left. Here I was having this plot at B is equals to minus 0.5. Now I have increased the value of B from minus 5 to 4, which has shifted my function from 0 to somewhat around minus 5. Right? Do you agree with this? So changing the value of W will help you to shift your function left and right. And changing the value of W, it will help you to change the orientation of your function. And changing the orientation of a function will give you a leverage, will give you an opportunity to change the slope. Getting this point?
Yeah.
Right? See,
Yes.
here my slope, here if you see that this function will look similar to step function, right? But here, as I have changed the value of W, as I have reduced the value of W, you'll see that my slope has changed. The only point which I'm trying to make here is changing the value of W helps to change the slope of your function. Changing the value of B helps to move your function left and right. Okay?
Yeah.
Okay. So now, just a small question here. At what value of X the value of function is 0.5? So for that, what I want is this functions to become 0.5, right? I want my probability value to be 0.5. So I'll equate it with 0.5 and you'll see that when my X is equal to minus B by W.
Okay.
Okay. Now, can you answer this question? If you have understood the last slide. The weight and bias of a sigmoid neuron respectively help in deciding which geometrical aspect of decision boundary. You have 4 options.
Slopes and midpoint of decision boundary.
Correct. The option
Third
third is
one.
correct. Yep. Okay. So far, anyone having confusion? No, right?
No.
Okay. Now coming to the another point. So we have seen the.
Ashutosh, I have one doubt here.
Mhm.
So, when you said like WX plus B is in the range of 0 and 1. So is it
Uh,
is there any other way to understand
wait.
how it is like?
I did not say Wx plus b is in the range of 0 to 1. I said after applying
Minus
sigmoid, applying
okay, after
sigmoid,
it was
yeah,
exactly.
wait.
Yeah, then
After, the value of y, yeah, the value of y is in the range of 0 to 1. This Wx plus b, it is not necessary that it will be in the range of 0 to 1. The moment you'll put that value in sigmoid function, it will squeeze it between 0 and 1. That is what I said.
so how do you put that in function like?
Okay. Okay.
So that is the question.
Okay. For that, I need
That
to
is still
come.
pending actually. I understood like how we draw that conclusion, but then how it is like that's still a question mark in my head.
Yeah. Okay. All right.
I hope you understood my question.
No, no problem. No problem. Let's take an example where I'm having two input, x1 and x2. Okay. And corresponding to this two input, I'll have two weights, w1, w2. Right. If you recall the formula, what we did is we have taken x0 and w0 also, where my x0 was equal to 1 and my w0 was equal to b, right? But for time being, let us not take this assumption. We'll just only have these two input parameters. Okay. First of all, what you have to do, you have to take a weighted sum of this, right? What will be the weighted sum of this? X1 w1 plus x2 w2, right? And you'll check if it is greater than equal to b. X1 w1 plus x2 w2 minus b greater than equal to 0, right? Now what I'm saying is, first of all, you compute the value of this. You compute the value of this. You just compute the value of your LHS. Forget about the RHS part. Compute the value of LHS. Whatever value you are getting after computing this, we are putting this value here in this place. Right?
What are the values here? Example.
See, your x1 w1, right? X1 w1 and x2 w2. Wait. I think I need to take a real data to make you understand this. Let's say that price, house price, right? This is the price of house, and this price of a house depends upon area. It depends upon locality, or let's say that number of bedrooms, just to make it an integer data. I'm taking only one observation. Let's say area is 1500 square feet. Number of bedroom is 3, and the price is around rupees 50 lakh. Okay. So what is your x? This is your x. This is your x1. This is your x2. Right? Corresponding to this x1 and x2, there will be w1 and w2. Let's say that w1 is equals to 0.5, w2 is equals to 0.2. Right? If you have to put these values into this equation, what will be the output? 1500 multiplied by 0.5, 3 multiplied by 0.2. What will be the answer of this? 75, 750 plus this is what, 0.6, 750, 0.6. This is what you have got after doing weighted sum, right? This value you have to put here. This value you have to put here, and this y will be any value which will always range between 0 and 1. Is it clear to you now?
But still, I feel I have not come to conclusion. Like if you see the complete mathematical part is missing to understand that the whole thing y is equal to is will be in the range of 0 to 1. So that is still
You can do
again
hit and trial. You can do hit and trial. Use
like how, see here. So that's a Euler number E. So
okay,
even if you substitute 750.6,
okay,
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 plus
okay,
B, and
okay.
here what is B here?
Here B is your that threshold value, right?
Okay, what is it like?
Forget about B also. Forget about B also. Just look at WX. B is constant. Forget
Okay,
about this
constant.
one. Yeah,
But
it
there
is a
should
constant.
be something applied to show that y is in the range. So I'm
Okay.
still missing this part.
Yeah.
So if that is still not clear, I'm sorry.
Okay.
If there are some softwares which plot the graph. So if you use them and just give the value of x, and you will be able to see how the graph is changing and what is the value of y. So you will be getting
No,
clear
it's
idea.
not about the graph. Like it's about the
Okay.
value of y, how it changes from 0 to
Wait,
1.
wait.
Graph I understood. Like how it is.
I'll make this clear to you. Although we have covered this one, let me explain this to you one more time. Here, see, what is the minimum value you can expect for this? What is the lowest value you can expect for this? Minus infinity?
Yeah, good. Yes, of course.
If you put minus infinity here, what will be your calculation? 1 upon 1 plus e raised to minus infinity. 1 upon 1 plus e raised to infinity. Right? This infinity is 2 point some value. It is a positive value, right? So
Mhm.
2 point something raised to infinity, it will be a very huge value, right? It will be close to
Mhm.
infinity. Any number which is very close to infinity plus 1 is what? Infinity itself. What is that?
Yes, less than
1 upon infinity, that is equal to 0,
yeah.
right? Now, coming, so if you think for the lowest value, the extreme lowest value, it is giving a value of 0. Now think of a highest value. What can be the highest value? Plus infinity, right?
Yes.
If I put 1 upon e raised to minus, here I'll put plus infinity. This value is will become almost 0. E raised to minus infinity is what? 0.
Mhm.
1 upon 1, this is equal to 1. So if you put the minus infinity, you are getting a value 0. If you are putting plus infinity, you are getting a value of 1. Any number you can think that will always lie between minus infinity to plus infinity,
Okay.
right?
Okay. Yeah.
So
Yeah.
that is why the value of y will be always between 0 and 1.
Mhm. Mhm.
Is it clear
So
now?
even if it is, yeah, I got it. Yeah. Okay. No problem.
Okay. Now let's get back to this. Okay. So if we talk about the data and task, so in case of our perceptron, we were dealing with categorical output, but here we will we can deal with numerical output also. So how do we relate it with real life? I'll take a same example of mobile phone. Earlier, we were thinking about whether you will like that phone or not, right? But now instead of your like or dislike, we're having other thing, which is your rating, right? So we can now predict, if I give you phone with this specification, how much you would rate it based on your previous rating data, right? So now we are no more restricted to binary output. We can predict numerical output also, right?
Yeah.
Okay. This question, can you answer? Why do we say that the sigmoid neuron can do regression?
Sigmoid is non-linear.
No.
It produces real
We
valued
say that
out.
sigmoid neuron can
Yes,
do regression.
it produces a real
It's
valued
only
output. That
in
is
the range 0, 1. Yeah.
Yep.
Uh,
Okay.
Ashutosh, can
Yeah.
you go back to that slide of the phones, right?
Yep.
Yeah. So here you change the output instead of binary, you changed it rating, right?
Yep.
Like 8, 7.
Yep.
Uh, since these are numbers are like whole number, I mean, they are
Hmm.
not between 0 and 1, right? These are like numbers, proper
Hmm.
numbers.
Hmm.
So we will get the result in between 0 and 1. So for example, if we are getting say 0.9,
Hmm.
that will imply that it's rated 9.
Yes.
Like
Yes.
that.
Exactly. Yep. Yep. Right. See, because see, these are not just absolute number. This is your rating, right? So you can say that a rating of 8 is equivalent to rating of 0.8. If you'll change the
Oh,
scale from 10 to 1,
okay.
right? So
Got it.
it is just a frame of reference. If you can see it at the scale of 1, then definitely you can apply it for Sectron model. Sorry,
Okay.
Sigmoid neuron. Yeah. Okay. Now coming to the loss function, right? So this is the third important part we have to see whenever we are dealing with any model. So initially we have seen square error loss, right? So in this case also we can live with a square error loss, right? So how does square error loss operate? If you look at this particular table, I have two cases, one for regression and another for his classification. For regression, this was my actual target. This is my actual label, but what I have predicted, I have predicted 0.6. So in this case, what would be my loss? My loss will be what? My loss will be 0.5 minus 0.6
Whole square.
whole square, right? The same will happen for here also, right? Now, in order to improve the accuracy of my model, what I need to do? I need to have this y cap similar to my y, right? In that case, only my loss will be 0,
Yeah.
right?
So one question, Ashutosh. So in the top table, right, where you have mentioned y and y cap 0.5, 0.6.
Mm-hmm.
Then you have mentioned that as regression. So the regression is when your prediction is not matching your target, right?
No, no, no,
That's
no.
when it's regressed. No.
Regression is a kind of problem where your target can take a numerical value. It can take a real value. Whereas
Okay.
classification is a kind of problem where your target, it can take categorical output. It can be 0, 1, 2, like that,
Okay. Okay.
right?
Got it. Yeah. So, sorry, I confused it with something else.
No, no issue, no issue. Now it is clear, right?
Yes. Yes.
Yeah. So in order to improve the accuracy of my model, what I need to do is I need to minimize this loss. What is the overall loss? The overall loss is the summation of all square error loss, right? So here in this case, my loss is this. In this case, my loss will be 0.8 minus 0.7 square. Likewise, I'll do calculate for all the cases and then I'll take the summation. That will be the overall loss, right?
Yeah.
And this loss should be as minimum as possible, right? So in order to get the best model, I need to minimize this function. Okay. In the next class, we will see how to minimize this
Yes.
function. In the next class, we'll see how to minimize this loss function, right? To get the best possible model.
So when you say minimize, you mean to say bring the value as less as possible.
Yes, ideally this loss should be 0. When my loss
Yeah.
will be 0, when my all y will equal to y cap.
Yeah.
But practically it is not possible, right? You cannot create a model which will give you 100% of accuracy. What we want is this loss should be as low as possible. And how this loss will be as low as possible? When my y cap will be as close to y, right?
Okay.
That
Yeah.
means I need to, and what y is composed of? Y is mainly composed of two things. One is w and other is b, right? You'll see that in this equation, what is this equation consist of? It is mainly consist of w and b, right? So if I able to find the optimal value of W and B, my Y will become close to Y and my loss will be minimized.
Can you come again? What you said?
My aim is to find that value of W and B that will make my Y cap similar to my Y or as close to Y, right?
Yeah.
Because if I'll have my Y equal to Y cap, my loss will be 0 and accuracy will be high.
Yeah.
Right?
Yeah.
So now in the next class, we will see how to get the optimal value of W and B. And that is nothing but Sigmoid learning algorithm. Okay. I'm gonna spin a bridge for 15 minutes. If you have any question, any doubt, or any recap you want, please join that bridge and we can get it clear there.